A passenger jet carrying more than 250 people is flying over the middle of the ocean. Below it, there are no cities, no highways, and no runways for hundreds of miles. Inside the cabin, the lights are dimmed. One passenger is watching a movie. Another pulls a blanket over his chest and closes his eyes. Flight attendants have just collected the final meal trays. Everything feels completely normal. Then, a sudden bang comes from somewhere near the left wing. The aircraft shakes. A brief flash appears outside the window, and the familiar sound of one engine suddenly disappears. Inside the cockpit, warning messages begin to appear. The left engine is no longer producing thrust. In this situation, the most suitable airport is still about 90 minutes away. And from this moment on, more than 250 people are depending on the only engine still running on the right wing. Many people believe that if an airplane loses an engine over the ocean, it will immediately fall out of the sky. But that is not what happens. The aircraft keeps flying. However, from that moment on, every minute forces the pilots to manage a shrinking margin of safety. Why did the engine fail? How much fuel is left? Can the aircraft maintain its altitude? And what happens if the remaining engine also shows a warning? Now, we're going inside the cockpit of a flight that has just lost half of its thrust over the open ocean. When passengers hear that an engine has failed, many assume that the machine keeping the airplane in the sky has stopped working. But engines do not directly hold an airplane in the air. The wings create most of the lift. As long as the aircraft maintains enough speed, air continues flowing over the wings. The difference in air pressure creates lift and keeps the airplane above the ground. The engines provide thrust. That thrust allows the airplane to maintain speed, climb, and overcome drag. When one engine stops working, the aircraft loses a large amount of thrust, but it does not lose its ability to fly. The remaining engine produces more power. The pilots use the rudder to counter the uneven thrust. One side of the aircraft is still being pushed forward, while the other side is not. Without correction, the airplane may begin turning toward the failed engine and losing additional speed. To the passengers, the failure may feel like a strong vibration, an unusual sound, or a slight bank. But inside the cockpit, the pilots are not focused on how the situation feels. They are focused on airspeed, heading, altitude, and control. Only after the airplane is stabilized can they answer the more dangerous question. Did the engine simply lose thrust? Or did something inside it break apart? One pilot continues flying the aircraft. The other reads the warnings, checks the engine data, and begins the emergency checklist. Is the engine temperature too high? Has the oil pressure dropped? Is the engine vibrating? Is there a fire or a fuel leak? The first step is not always to restart the engine. The first step is to confirm exactly what happened and which engine is affected. In a high-stress situation, shutting down the wrong engine could turn a serious problem into a disaster. If the failure appears temporary, the crew may consider restarting it. But if the engine is overheating, vibrating violently, or showing signs of fire, it must be isolated. Fuel flow is shut off. Related systems are disconnected. And if necessary, the built-in fire suppression system is activated. When one engine stops working, the airplane becomes like a city that has suddenly lost one of its power stations. The remaining systems must take on additional work to keep everything essential operating. Electrical power is redistributed. Flight controls remain available. The remaining systems are configured to support critical functions, including cabin pressurization. The aircraft is still flyable, but an important layer of redundancy is gone. From this moment on, every change in the remaining engine is watched as if the entire flight depends on it. Because it does. And while the engine data continues moving across the cockpit screens, the pilots must make the most important decision of the flight. Where can they land? Over land, an airplane in trouble may have several airports nearby. Over the ocean, the nearest runway may be located on a small island or hundreds of miles away. Long-distance oceanic flights are not planned randomly. Before departure, the airline identifies a network of alternate airports along the route. But the pilots cannot simply look at a map and choose the nearest dot. They must ask several questions. Is the runway long enough? Is the weather suitable? Is the crosswind too strong? Can the airport handle this type of aircraft? Are emergency crews available? And most importantly, Is there enough fuel to reach it with a safe reserve? The nearest airport may be covered in fog. Another airport may have a runway long enough, but strong winds could make the approach dangerous. A third airport may be farther away, but have better weather, a longer runway, and full emergency support. While the pilots, air traffic control, and the airline's operations team compare the available options, the aircraft continues burning fuel. Every minute has a cost. Eventually, the crew selects an alternate airport ahead of the aircraft. In this situation, it is about 90 minutes away. The original journey is now over. From this point forward, the goal is no longer to reach the planned destination. The goal is to reach a safe runway before another problem appears. With both engines operating, the aircraft can maintain its cruising altitude efficiently. But one engine may not always produce enough thrust to keep a heavily loaded airplane at the same altitude. That depends on the aircraft's weight, air temperature, wind, and engine performance. If the airplane cannot maintain its current altitude, the pilots begin a controlled descent. This is not an uncontrolled dive. The aircraft descends at a calculated speed until it reaches an altitude where the remaining engine can support stable flight. At a lower altitude, the air is denser. Denser air helps the wings produce lift, but it also creates more drag. The remaining engine has to work harder. Fuel consumption may increase, and the original flight plan must be recalculated. Inside the cockpit, the pilots are now watching three things continuously: the distance to the airport, the fuel remaining, and the condition of the only engine still operating. Temperature, oil pressure, vibration, rotational speed. Every value must remain within limits. The pilots do not assume the second engine is about to fail, but they are also not allowed to treat it as invincible. More than 250 people are depending on a machine spinning at enormous speed outside the right wing. If it remains healthy, the aircraft should reach land. If a new warning appears, the entire plan could change within seconds. Inside the passenger cabin, the captain makes an announcement. The aircraft is experiencing a technical issue. The situation is under control, and the flight will divert to another airport. The announcement is usually calm and brief. Passengers do not need a lecture about oil pressure or turbine temperature. They need to know what they must do. Flight attendants begin checking the cabin. Carry-on bags are secured. Seat belts are fastened. Aisles and emergency exits are kept clear. If the airplane has only lost thrust and remains stable, the landing may feel similar to a normal arrival. But if the failed engine experienced fire, severe vibration, or possible structural damage, the crew may prepare for an emergency landing. Flight attendants review their responsibilities at each exit. Passengers may be instructed to assume the brace position. On the ground, fire trucks and rescue crews begin moving into position. Outside the windows, there is still nothing but ocean. The airport remains nearly an hour away. For the passengers, time seems to slow down. Inside the cockpit, the pilots continue updating the weather, wind, fuel estimates, and engine condition. Every minute brings the airplane closer to land. But the safety margin is no longer as wide as it was at takeoff. And there is one scenario that every airline pilot trains for, even though no one expects it to happen. What if the final engine also stops? This would be an extremely rare event. The crew does not believe it is about to happen, but pilots are still trained to handle it. If the remaining engine loses thrust, the airplane does not immediately fall straight down. It becomes a giant glider. The wings continue producing lift as long as the aircraft maintains enough airspeed. The pilots lower the nose to reach the best gliding speed. Altitude is now converted into distance. The higher the airplane is, the farther it can glide. But over the middle of the ocean, even that distance may not be enough to reach a runway. The crew would attempt to restart an engine if conditions allowed. They would check fuel flow, ignition, electrical power, and airflow into the engine. If the shutdown was caused by a temporary issue, the engine might restart. If the problem was serious mechanical damage, the chances would be much lower. In the worst possible case, the pilots would have to prepare for a water landing. They would evaluate wind direction, wave height, and the condition of the ocean surface. Then they would try to bring the aircraft down at the lowest practical angle and speed. But that is the final option. The entire system of long-distance airline operations is designed to prevent the flight from ever reaching that point. Engines are monitored and maintained. Routes are planned around alternate airports. Extra fuel is calculated, and pilots practice engine failures in full-motion simulators. In most single-engine failure events, the remaining engine continues operating until the aircraft reaches land. But after more than an hour of diversion, the coastline finally appears ahead. The flight is not safe yet. The wind at the airport is blowing across the runway. An airplane flying on one engine reacts differently whenever power changes. Each time the pilots adjust the remaining engine, the amount of asymmetric thrust changes. They must use the rudder continuously to keep the aircraft aligned. The flap setting must also be selected carefully. More flaps allow the airplane to fly slower, but they also create additional drag. That forces the remaining engine to work harder. Fewer flaps reduce drag, but increase the approach speed and the amount of runway required to stop. The pilots choose a configuration based on the aircraft's weight, runway length, and current wind. Below them, the runway has been cleared. Fire trucks are waiting on both sides. If the approach becomes unstable, the crew can still go around. But a go-around on one engine requires additional thrust, additional fuel, and precise control. It is not a decision the pilots want to make at the last second. The aircraft descends. 1,000 feet, 500 feet. A crosswind pushes the airplane slightly away from the centerline. The pilots correct. 100 feet. The remaining engine changes power. The asymmetric thrust changes with it. The rudder keeps the aircraft aligned. The main landing gear touches the runway. The airplane shakes. The brakes begin working. The speed drops. And after more than an hour with only one operating engine, the aircraft finally comes to a stop. For the passengers, it may be the most frightening flight of their lives. But the safe landing is not a miracle. It is the result of multiple layers of protection prepared before the aircraft ever left the ground. The airplane is designed to continue flying after losing one engine. The pilots train for this exact event in simulators. Alternate airports are selected in advance. Extra fuel is calculated, and critical systems have backup options. The remarkable thing is not that a machine can fail. Every machine can fail. The remarkable thing is that the aircraft, the crew, and the entire operating system were prepared for that failure before it ever happened. Losing one engine does not mean losing the airplane. But from that moment on, the pilots, the remaining engine, and every backup system must work together with extreme precision to bring hundreds of people safely back to the ground. If your airplane had lost an engine and still had 90 minutes to fly over the ocean, how much information would you want from the captain? Every technical detail, or only what you needed to stay calm and safe? Tell us what you would choose in the comments.